Hi guys, and welcome to video 29 in the But How Do It Know companion video series. And today we're going to be looking at I/O instructions and devices. So I/O instructions are used by the computer programmer when he wants to interact with external devices. For example, reading a keystroke from a keyboard, displaying a character on the screen, saving a byte of data to a hard drive, or any other interaction with a part of a computer that is external to the CPU. The format of the I/O instructions is as such. The first 4 bits are always 0, 1, 1, 1. The last 2 bits indicate the register that is to be used for the current operation. That register is used to transfer data to and from the I/O device. So in certain instructions it's going to be used to write to, and in others to read from. Let's call it RegB. The 5th bit indicates if we are doing input or output. 0 is for input and 1 is for output. Finally, bit 6 indicates if we are sending or receiving I/O data, in the case it's 0, or an I/O address, in the case of 1. So this may seem a bit confusing, and when I first came across this set of instructions in the book, it took me a while to figure them out. But in fact, it is simpler if we give each sub-instruction a distinct name. Take a look at the following table. I have reordered the instructions here in an order that is closer to how you would use them in a real program. So each I/O device that is connected to a computer has a unique address. If you want to interact with a specific I/O device, you need to refer to it using that address. So the first thing that you need to do to interact with an I/O device is to activate it. Device activation is done using the OUT-A instruction here. So the OUT-A instruction will activate the I/O device whose address is in RegB. Once your device is activated, you can then write to it or read to it depending on the kind of I/O device that it is. If you want to send a byte to the currently activated I/O device, you would use what is called here the OUT-D instruction. That would send the byte of data that is in RegB to the active I/O device. If you wanted to receive or read a byte of data from the currently active I/O device, you would use what is called here the IND instruction, and you would receive a byte of data into RegB. Finally, the last I/O instruction is called INA here, and it is used in the process of interrupt handling. So we are not going to be using this instruction here, and our CPU doesn't know how to use it. But how does our CPU communicate with external I/O devices? This is done through something called the I/O bus. So the I/O bus is comprised of these 5 elements. Each I/O device must be connected to the I/O bus and must be able to write to the CPU bus. The CPU bus is the same data bus that we have on our project board that connect all the pieces together. The I/O components can also read and write to that bus. Next are 4 control signals. The first 2 are input, output, and data address, and those correspond to bits 5 and 6 of the I/O instructions. Then you have I/O click E, which is used to indicate to I/O devices that if they have something to say, now is the time to say it. And finally, I/O click S, which is meant to indicate to I/O devices if they have something to read, now is the time to do so. It is the control unit's job to maintain the 4 signals in the I/O bus, and in our project board, this is done through the microcode. The 4 control signals that have white LEDs in our control section are I/O set, I/O enable, I/O input or output, and I/O data or address. The Arduino is listening to those signals because it is implementing I/O devices in software. More on those a bit later. But how are I/O devices meant to react to the different signals on the I/O bus? What is the protocol to be followed? Again, we will use a truth table to look at the possible combinations. Now imagine a random I/O device that is just sitting there listening to what's happening on the I/O bus. There are only 3 cases when it is expected to actually do something. If the CPU is processing an OUT-A instruction, and the I/O set signal is on, the device wakes up and reads the byte of data that's on the CPU bus. If the byte of data corresponds to its own I/O address, it activates itself. If not, it deactivates itself. Then, if the CPU is processing an OUT D instruction and the I/O set signal is on, the device reads the byte of data on the CPU bus if and only if it is activated. Finally, if the CPU is processing an IN D instruction and the I/O enable signal is on, the device writes a byte of data on the CPU bus if and only if it is activated. So each I/O device must have the proper circuitry to decode all these different signals, and this is well explained in the book. It also must have a 1-bit memory that it uses to remember if it is currently activated or not. If all the I/O devices connected to the I/O bus follow these rules properly, the CPU can coordinate all the I/O activity correctly. Now let's take a look at the I/O devices that are implemented by our Arduino. There are 5 I/O devices that are implemented inside the Arduino code. The first 4 are TTY or terminal devices that are used to read or write data to and from the Arduino serial monitor. The last one, device number 5, is a random number generator. Let's look at each of them in more detail. So if you use device 0 and you use it as input, it will read a character from the Arduino serial monitor and write its ASCII code to the bus. So for example, if you had typed the number 9 in the Arduino serial monitor, you will get the binary value 57 on the bus. If you use it as an output device, it will write the byte that is on the bus to the Arduino serial monitor as an ASCII code. So if you have placed the binary value 65, for example, on the bus, it will give you a capital A on the Arduino serial monitor. Device number 1 behaves similarly, except that it interprets the binary values as numbers. So if you type number 9 in the Arduino serial monitor, you will get the value 9 on the bus, not its ASCII code, its numeric value. If what you have typed is not a number, you will get 0. If you try to output to it, it will take the value on the bus and try to use it as a numeric value. So if you have binary value 65 on the bus, you will get the string 65 in the Arduino serial monitor. So this TTY makes it easier to input or output numbers without having to do the conversion yourself in your code. Device number 2 is exactly the same as device number 1, except that when you write numbers to it, it will pad them with spaces. That will allow you to create a nice table if you have many lines. Device number 3 is exactly the same as device number 0, except that it will insert a new line after every character that you print. This is useful to quickly write some characters and have them on separate lines. And finally, device number 5 is a random number generator. So if you try to read from it, it will print a random byte on the bus. So if you want to do a game, or if you want to do something that involves some randomness, you can use that. So that's it for the I/O part of our project. In the next video, we'll be looking at our assembly language and also how to make our clock run automatically. See you soon!